Today's topic is nucleus. A nucleus consists of electrons, protons, primarily. Electrons are negatively charged particles, charged bodies. Proton is positively charged bodies, and neutrons they have no charge. Weight-wise, they are very similar to each other in weights, where electron is much lighter compared to proton or neutron. Okay. Now, all these items are weighed in not in terms of kilograms or grams, but in a standard unit called atomic unit. And what is an atomic mass unit? It is equivalent to the mass of 1/12 of a carbon atom, which contains basically 6 electrons, 6 protons, and 6 neutrons. They together, whatever is the mass, 1/12 of this mass is called one atomic mass unit. Okay. So all these constituents are weighed in terms of atomic mass unit, also known as AMU, or sometime in short it is simply written as U. Now, some basic terminology and symbols. When we write, for example, an atom, and then we write this is the name of the element. This is the Z value, and this is the A value. Z is the atomic number, and A is the atomic mass number. Z is also equal to number of protons, and A is also equal to Z plus number of neutrons. So basically, this atomic mass unit is a sum of number of protons and number of neutrons put together, where Z is purely a number of protons, and protons are positively charged bodies. So this is just a convention of representing. Now there is some other terminology. Isotopes. Are variants of an atom with same number of protons, but different number of neutrons. So two elements who have the same number of protons, but the number of neutrons are different. That's called isotope. Next is isotones. Isotones are two atoms with same n, number of protons are same, but different atomic number. This is number of protons. Neutrons are same, but protons are different. Then we have isobars. They are atoms with same mass number. Mass number means atomic mass number A. All those atoms with equal A are isobars. The next topic is, let's try to calculate nucleus radius. Nucleus radius is defined as, this is a constant. This is A. A is nothing but atomic mass unit. Or atomic mass number, which is a sum of protons and neutrons. Now, the volume of nucleus will be, which is equal to, take R from here. Okay. So this is the volume of the nucleus. And if we take m, which is the mass of the nucleus, this is equal to, this is the atomic mass number and this is mass of proton, and mass of proton is very nearly equal to mass of neutron. So if we find out the density of nucleus, will be given by mass, which is this much, and volume, which is given by this, which is So this gets cancelled away. What you get is 3m . Now here everything is constant. This is constant. This is constant. Everything is constant. So this is constant. From this equation, what we say is that density of a nucleus is constant. Is a constant value. It doesn't depend upon atomic mass number. Now we talk about nuclear forces. Nuclear forces are much stronger than Coulomb forces. You see, nucleus, you have a lot of positive matter, lot of neutrons is okay, but these positive charge protons would try to repel from each other as per the nucleus Coulomb's forces, but they are bound together by nuclear forces. So nuclear forces are much stronger. These nuclear forces are much stronger than Coulomb forces in a nucleus, of course within a range. They are strong within a certain range. Which is also known as nuclear range. So you have forces between neutron-neutron, proton-proton, proton-neutron. These are all the forces which are present in a nucleus. And in nuclear forces, are independent of charge. This is very important. Nuclear forces are independent of charge, meaning thereby whether we talk about proton-proton or proton-neutron, they are nearly same. All these forces are nearly same. Now next comes binding energy. An atom is held as a stable unit. And if you want to break it, you need some energy to break it. Okay. Now this energy required to break it is called binding energy. And binding energy, we can find out by doing some mathematics on the rest mass of its constituents. For example, binding energy can be given as mass into mass of a proton plus mass of a neutron minus m. This is the total mass of proton, because this is unit mass of proton into number of protons, and this is number of proton into unit mass of proton minus m. M is the mass of the nucleus. Now you might be wondering that this is nearly totally the mass of the nucleus, and then why it is different from mass of the nucleus? Yes, it is. Because when the constituents are bound together, the total mass becomes less. Now this can be rewritten as this Z, which is mass of proton, we can replace it with mass of hydrogen atom with Z is equal to 1 and A is equal to 1. Means it has one proton and one proton plus neutron. And mass we can represent in a generic form as Z, A, which is equal to Z plus N. Okay. Now we define another term, binding energy per mass number, which is equal to A1 minus A2 minus A3 This is the formula for binding energy per atomic mass number. Here A1, A2, A3, they are all constants. Z we know is the number of protons and A is the atomic mass number. So this is the formula which is given. The next topic is mass excess. What is mass excess? This is the difference between actual mass of an atom and its constituents. Meaning thereby, we have a nucleus where we have protons, we have neutrons. If, for example, let's take A dash as an atom has atomic, this is atomic mass number. Then obviously its weight as per atomic mass number will be atomic mass number into mass of one unit. Okay. And let us say the actual mass is m mass units. So its total mass will be so much. So we have two weights. One is this one and one is this one. And what is the difference between the two? The difference between the two is it's called mass excess. This is defined as actual mass minus mass as per atomic mass number. This is nothing but this mass excess is in terms of energy, because as per Einstein's, E is equal to mc squared. Actually, this mass excess is coming because of this reason, that mass is convertible to energy. And if the energy between two entities are different, although they might have started with the same mass, the energy part may contribute something to their mass as well. So the excess mass, which is this much, can be written as so you see, the difference is coming because of this is the actual mass in terms of AMUs, and this is the mass as calculated by our mass number. Remember, we have, when we write X, Z, A, this is the atomic number. This is the atomic mass number, which is nothing but A is equal to Z plus number of neutrons. So we can say this is calculated as per the constituents, and this is mass of the nucleus as a whole. Now we are not talking about as a constituents, whereas this is the value which has been calculated from the constituents. So there's a difference between the two, between the constituent and the whole mass. And this is coming because of a factor called energy, which is making these two entities different. Okay. Now, let's talk about alpha decay. When an unstable atom loses 2 protons and 2 neutrons to become more stable atom, what happens in between is, let's see if, as an example, we take bismuth, which is Z is equal to 83 and E is equal to 212. It can break to titanium 51208 plus helium, which is 204. So if you see, the bismuth has lost from 212 to 208. This is A. And what is the difference between protons? It has lost 2 protons. Protons lost is equal to 2 and neutrons lost is also 2, because the difference between A value is 4. So total difference will be 2 plus 2 is 4. Okay. Now, if we want to find out the energy released in this process, which is Q, we have to find the difference between initial and final near rest mass. This is final rest mass. This is initial rest mass. Now, how much will be the initial rest mass? Initial rest mass is, because of Bismuth only, which will basically be mass of Bismuth or whatever element it may be with this much, and it loses 2 protons and 2 neutrons. So it becomes another element with Z minus 2 and A minus 4 minus the weight of the helium atom. So this is the difference in energy levels, C squared. This is the initial rest mass unit, the rest mass, and this is the final rest mass. The difference between the two into C square is the energy which is released in this process. Now in this process, you see this helium, this is nothing but our alpha particles. Alpha particles are basically helium atoms without any electron. So alpha particles are basically helium atoms. Now in this process, the alpha particles are released and the energy that is released is given by this equation. And the basic premise was that why did it happen? It happened because atoms with heavier A, with more A, meaning the bigger the atom is, more it tends to be unstable. So normally if A is greater than 207 approximately, the alpha decay takes place all the time. Because when the atomic mass becomes greater, the nucleus, the atom is no more in a stable form. It tries to become stable form by shedding 2 protons and 2 neutrons. So it becomes slightly lighter, and in the process, alpha particles are released in the form of energy. And the energy that is released is given by this formula. Similarly, there is another form of decay which is called beta decay. It has two forms. One is negative beta and one is positive beta. Let's talk about beta negative. Now here what happens is that a neutron tries to become a proton by shedding one electron and anti-neutrino. So basically a neutron is trying to become a proton. And in this process what will happen? Since proton is a positive charged material, to balance an electron has to be shed, right? Now as an equation we can see that let there be an element X with Z protons, and here is the atomic mass number going to Y, in which number of Z is increasing because neutron is becoming proton. So proton number has increased by 1. And atomic mass number remains same. So if you want to find the energy released in this process, what is initial mass and rest mass? Initial rest mass is now now what we are trying to find out is the mass of the nucleus. This is the mass of the atom. So we have to subtract the mass of the electrons from it. And how many electrons are there in? Is the same as the number of protons. So if we take out the mass of electrons, this is the mass of the nucleus initial. And what is final rest mass? Final rest mass is Y. Similarly, this is, and we have to take out. Now it will contain Z minus 1, Z plus 1 number of electrons. Plus what you have got is, we got one another electron. So this is mass of electron. So what we get is and the difference is nothing but so this much of energy will be released when a neutron becomes proton in this reaction. One electron is released, and this is beta nucleus. Because of this extra electron which is coming out makes beta rays, which are beta negatively charged rays, and the energy released is given by this formula. There is a small correction. Instead of this whole bracket, this bracket should end here. So basically what we are saying is this is the mass of the atom minus the mass of the electrons because of these Z+1 protons, plus we are getting one electron extra. So this final is okay, but this bracket should be shifted here. Okay. Now what may happen in beta plus decay, the reverse happens, meaning a proton becomes a neutron. Proton is a positively charged item. When it becomes neutron, there is some extra positive charge which is released as this. This is called positron, and this constitutes our this is beta plus and now we do the same treatment to find out the shift in energy levels released in these reactions. Let's assume there is an atom X with Z, and then a proton has to become a neutron. That means there is a decrease in number of protons. So if it becomes Y, number of protons becomes less. This remains same. This mass of positron is nearly same as mass of an electron, approximately. So if we say this is beta plus decay. Now let's calculate the energy released in this equation. This is the initial mass, rest mass. And if we take out the weight of the electrons from both the sides, what we get is 2 extra electrons in the final product. 2C2. So this much energy will be released when any element loses its proton to become a neutron. And this results in a beta plus decay. Another form of change in nuclear structure is by way of electron capture. What happens? Nucleus captures most likely an electron from kth shell. And in this process, what happens? A proton plus an electron makes, this is positively charged, this is negatively charged. When they combine together, they make a material which is electrically not charged. It doesn't have any electrical charge because it's a neutron. As an example, you take an element X with Z proton, atomic mass number, with one electron, it makes the number of protons less by 1. And if we calculate the energy released in this process will be rest mass of A minus rest mass of C. This much energy is released when the nucleus captures an electron from slightly loosely bound energy level, which is a K shell. In this case, what happens? Obviously, a proton, the number of proton decreases, so value of Z becomes less, and in this process, so much of energy will be released. Now, what happens is, when an electron is captured, a vacancy is created. In atomic shell. And X-rays are emitted. Now, another type of decay is gamma decay. See, in alpha or beta emissions, the daughter nucleus is in excited state. If a nucleus is in an excited state, it cannot remain so for a long time in that state. And what happens is, it tries to go to a stable state. And while doing so, it releases energy. And this energy is released in the form of photons. which are neither positively charged particle nor negatively charged particle. They are just energy packets, which we have seen that they have energy called capacity of H. And since this is the photon, this is electromagnetic radiation. So gamma rays are also electromagnetic radiations because the energy released is in the form of photons. Now, just an example, if you take copper 57, which releases beta plus rays, and it comes to 136 kiloelectron volts. And the next level of energy is 14 electron volts. And the last is ground level, which is 0 electron volts. So what happens is, when an excited atom, excited nucleus, whatever you call it, releases beta rays, it is already in an excited state. Now, what happens is, from this state, there are three ways it can go. One is, it can go directly from here to here, or it can go directly from here to here, or having come to this place, it can go from here to here. And each of these processes, it releases energy in form of photons, they are called gamma rays. So we know mu can be converted into lambda. So lambda is equal to h. This is the wavelength of the gamma rays which are released in any of these processes, depending upon which level it is shifting from to which level it is shifting to. As we have seen in gamma rays, there is no change number of proton or neutrons or protons. Number of neutrons or protons remains same. Now we have seen all alpha, beta, gamma radiations decays. Decay means we get their respective radiations. Now, any material capable of undergoing radioactive decay is called radioactive material. So what is a radioactive material? Radioactive material is one which will give rise to either alpha, beta, or gamma rays, which are radiations, for whatever reasons. And when it does so, this material is called radioactive material. Now let's see the speed of decay. The dynamics of radioactive decay. We know this is the number of active this is number of active nuclei. This is the basic equation of decay, because it is the number of active nuclei are becoming lesser because of this sign negative. So the active nuclei decay and the rate at which it happens is given by this formula. Basically, it is proportional to number of active material present at any time t, and this lambda is called decay constant. Okay. Now, if we take this basic differential equation, and if we do what we'll get is we get an equation says this is number of active nuclei remaining, and this is the number we started with. This is the number which remain, which are left out at time t. So this is the formula. And similarly, we define another term where A is the number of disintegrations per second. So number of disintegration at any time t is given as number of disintegration at time t0 when you started with, and this is the number of integrations after time t. Okay. Now there is another term called specific activity. Is given by activity per unit volume. Now in radioactivity, there is a very important term called half-life. As the name suggests, half-life, meaning thereby what is the time? This is equal to time taken to shed mass by half. Let us say if we started with 50 grams of any radioactive material, how long will it take so that this 50 grams remains to 25 grams? Or if we take 10 grams, how long it takes for this material to decrease to 5 grams? The time taken is is called half-life. Okay. Now, if we use our basic equation that number of active nucleus at any time t is given by this formula, which we saw here, then if nt is half of this, and if we solve this equation, what we will get is that t half is equal to ln 2 by lambda, or ln 2 is 0.693. This is a very important relationship that through which you can calculate your half time. Basically, half time is equal to ln 2.693 divided by lambda. Lambda is the constant value. We can also write t in terms of half-life, which is 2 power t divided by. We rarely use this form. We are more comfortable using this particular form. Now we have calculated half-life here. Half-life is basically time taken for the initial material to reduce it to 50% of its original weight. Now, similarly, we can find out what is the average life. We know dN by dt is equal to this was our basic equation. Using this basic equation, if we expand, what we will get is that T average is equal to 1. T average is average lifetime, average lifetime. So T average is also given as this is a more convenient form of which is in terms of half-life. Average life can be given as in terms of half-life by this formula. Now there are certain properties of alpha beta monomers. Now, if we talk about alpha rays, as we have seen during alpha rays, alpha particles are released, and alpha particles are nothing but helium nucleuses. And since this is not a neutral helium nucleus, this is helium nucleus without any electron. If it is not without any electron, then definitely it will have a net positive charge, double positive charge. So it is positively charged. If it is positively charged, obviously it will be deflected by electrical as well as magnetic field. It has low penetration power. It has large speed. And all alpha particles coming from a particular decay. Particular decay means decay of one particular element. If they are coming from same element, then all alpha particles will have same energy. And when alpha particles are released, they produce scintillating flashes. Scintillating flashes what? I don't know. If in a night you take out your pullover, you will see some light flashes coming out. It's because your pullover, which is a woolen pullover, develops some charges. And when the charges try to neutralize, they discharge and produce some sort of a light. Okay. And since it is positively charged particles, they can cause ionization in gases. When we come to beta, beta rays, and we have seen in case of beta minus, in the product we were getting an extra electron, which we call beta rays. So it's a stream of electron coming from nucleus, yes. Since it is made of negative charge, again, because this beta rays is nothing but stream of electrons coming out of the reaction, it can be deflected by electrical as well as magnetic field, obviously. And it has more penetrating power than alpha particles, and it has less ionization power compared to alpha particle. It provides scintillating effect, but not as much as alpha particles provide. And another thing which is different from alpha particle is that energy of beta particles coming from the same decay are not equal. All the beta particles coming from the same decay, they may not be same. And this was for beta negative rays. For beta positive rays, properties are more or less same, except that they are made of positive charge. Because what we have seen is that it produces A plus, which are basically positive, which are positively charged particles. Gamma rays, we have seen that it is the only ray which is electromagnetic minded. And it is, since there is no charge in gamma rays, it's purely energy. So obviously it cannot be deflected by a magnetic or electrical field. It has no charge, so it has least ionization power compared to alpha or beta. Since it is electromagnetic wave, it can travel at the speed of light in vacuum. And it is usually used in cancer therapy. In medical surgeries, gamma rays are also used as a knife because it has very high penetrating power. And gamma knife, as against mechanical knife, can cut through the tissues very easily because its penetration power is very high. Okay. Next topic is fission. What is a fission? When we bombard a nucleus with neutron. For example, if you take one neutron and bombard it on uranium-235, uranium-235 breaks down into barium and krypton atoms. And interestingly, what happens in the process, one neutron bombarded a uranium, and instead in the process, 3 more neutrons are formed. Now what happens is, if this keeps on happening, this will keep on going in a chain, and very fast chain reaction will happen. Yeah. Another example is this, wherein U-235 is breaking down into Sb and Nb with 4 neutrons coming out. So here are the 3 neutrons coming out, here is 4 neutrons coming out. And the fragmented product which is produced, for example, barium, krypton, or Sb or Nb here, they are highly radioactive and unstable. Their radioactivity and emit beta particles in succession until each one becomes stable. And usually, while it is stabilizing to a stable state, a lot of energy is released. And where does that energy go? Basically, this energy is available to surrounding as heat energy. Now, if the neutrons which are liberated, for example, 3 numbers here and 4 numbers here, they are not slowed down, they will escape from the reactor. Okay, without interacting with any other uranium nucleus. So in order to slow down, what is done is we used substance called moderator, which is like water, heavy water, and graphite rods, which basically try to absorb neutrons. Okay. Then to find out how fast is this fission reaction, there's a term called K, which is a multiplication factor. Multiplication factor is the number of fission produced by a generation of neutron to the number of fissions of the preceding generation. Meaning thereby, for example, this was one generation and this is the second generation. So this generation produces one fission, and how much is the product neutrons going to produce number of fissions? The 2 ratio is called multiplication factor. If this multiplication factor is 1, nuclear reactor is critical. If it is greater than 1, meaning by it is very fast multiplying, and the reactor power will increase almost exponentially. And if you don't control it, you may go into a runaway reaction. And to control it, what we have to do is we have to moderate by cadmium rods as an absorbent. Now, as opposed to fission, in which an atom is broken down into 2 smaller atoms, in fusion, 2 atoms are combined to make a bigger atom. For example, we have hydrogen with atomic number 1, atomic mass 1. They combine together to form another hydrogen atom, deuterium, with same atomic number but twice the number of atomic mass. And in this process, so much energy is released. And there are various reactions in which different level of energies are released. In all these reactions, two positively charged particles combine to form a large nucleus. Two positively charged atoms, both are positively charged, combine to form one large nucleus. And obviously, the reaction has to overcome the Coulomb repulsive forces. And to do this, this happens under very high temperature of the order of, let us say, 3 into 10 to the power 9 degree Kelvin. So the first process where an atom was breaking into smaller atoms was fission. Fission means breaking, and opposite to that is fusion. Fusion means combined, combination of two. So two smaller atoms are combined to make a bigger atom. This is nuclear fusion.